Okay, good morning. Today we will discuss about the measurement of surface tension and then we'll start our discussion on uncertainty analysis. Whenever we deal with the fluids, we have to actually also take into account the variations in properties of the fluid. So, typically, the common properties of the fluid, such as density, viscosity, specific heat, enthalpy, internal energy, all these properties are something which are specific to a particular fluid medium. Okay, whereas surface tension is a property which only comes into account when fluid is interacting with another surrounding phase. So it's a property of a fluid pair rather than a single fluid. So we have already good understanding about other properties such as density, viscosity, pressure, temperature, etc. through our basic courses such as fluid mechanics and thermodynamics. We also know about surface tension particularly in the course of fluid mechanics, and whenever we study that in under that particular course, our major interest is in determining the surface tension of different liquids in the presence of surrounding air. But whenever we will be going for the multi-phase flow situations, then always the surrounding phase will not be air. So there can be many possibilities where two liquids are actually participating in such a way so that one liquid is acting as a dispersed phase and other is acting as a continuous phase. There can be scenarios where liquid is present in the surroundings of its vapor and liquid is present in the surroundings of some other gas which is not having constituents of air. So under these scenarios, we will not be finding any standard data available from where we can actually get the value of the surface tension. So that's why for studying multi-phase flow situations, if our fluid combinations are such that for which there is no data available in the literature, in that scenario we have to measure the surface tension for the two different fluid combinations. So that is what we will try to see over here. So if you see the origin of surface tension, it comes from the molecular behavior, where you can see if you have a molecule which is present in the bulk of the fluid medium, that molecule will be having interaction forces, attraction forces from the surrounding molecules, and as this molecule is present in the surrounding of the similar type of molecules, therefore the nature of the interaction forces will also be remaining the same. Other than the presence of the nature of surrounding molecules, it also depends that how closely or how sparsely the molecules are placed. We know that if we have to consider the intermolecular potential for intermolecular forces phi as a function of intermolecular distance r, then we know that whenever the molecules are far apart from each other, then these are having very weak interaction forces. Whenever these are coming close to each other, then the magnitude of the interaction forces starts increasing. It reaches a peak value. After that, the attraction forces starts decreasing, and below certain critical distance these forces becomes repulsive nature. Okay, and one important point we have to see over here, when we are considering the zone of attraction forces, then a wide spectrum of R is available in which the attraction forces are actually coming between the molecules. So that's why the attraction forces which are there in between the molecules, these are called as long range forces. On the other hand, if you talk about this particular zone, so here you can see the spectrum of R is actually very small, and in very small distance of R, the force is changing by significant amount. So first point is the nature of this force is repulsive, and second important point is that this entire force is changing significantly over a very narrow spectrum of R. That's why these forces are called as, actually these repulsive forces within the molecules are called as short range forces. And typically if you see, all these forces are majorly caused due to three effects. First effect is electrostatic effect. Second effect is inductive effect. And third effect is dispersive effect. So why these intermolecular forces comes between the molecules? That majorly comes either because of the electrostatic effect or because of inductive or dispersive effect. So typically if we see a molecule something like water, so what happens in case of water? It is something like this. Now this O molecule is more electronegative, so that's why it will be having some permanent delta negative charge, and hydrogen molecules will be having permanent delta positive charge. So because of this, what will be happening? There will be a permanent dipole which will be existing in this molecule. Okay, so whatever the effect is caused by this permanent dipole, that particular effect is something which comes under the category of electrostatic forces. So ultimately what will be happening? Because of this effect, whenever water molecules will be arranging each other, these will be leading to formation of hydrogen bonds. Okay, so that is coming because of the electrostatic nature. Now there are some molecules, so likewise if you consider other molecules such as all alcohols, like if I give you example with methanol, so I will be having some hydrogen bonds, and then I will be having over here OH bond, and particularly this potential and this will be creating the significant dipole over here. Okay, so once you have the presence of net dipole moment, under that scenario we will be finding that we will be having electrostatic interaction. So there are some permanent charges which are existing on different atoms of the molecule, and when these molecules are interacting with the surrounding molecules, so because of these permanent charges there will be some forces. So whenever these are far apart from each other, so molecule will orient in such a way so that the positive and negative opposite charges are facing each other, and mostly the nature will be attractive, but whenever these are coming close to each other, nature will be repulsive. When we talk about the inductive effect, inductive effect typically comes when a permanent dipole molecule induces charge in neighboring neutral molecules. Okay, so if you have a permanent charged molecule, whenever it will be coming in close contact with the neighboring neutral molecule, then in neighboring neutral molecule also some type of charge will be actually generated, and that charge ultimately may lead to attraction and repulsive forces between the molecules. So that effect is called as inductive effect. And final effect is dispersive effect. Dispersive effect mainly occurs due to the instantaneous charge fluctuations in particularly in atoms of the molecules. So we know that around the atoms, electrons are actually continuously oscillating. So in such certain conditions, if electron is moving out of the field or entering into the field of other atom, in that scenario, some temporary charges are induces. These temporary charges does not stay for long. These comes frequently. So this type of fluctuating charges which are there on the atoms, these comes under the dispersive effect. Mostly whenever we study all the polar molecule, because surface, what is surface tension? Now you have seen over here that I have explained you what is the reason for attraction and the repulsive forces. Okay. Now if a molecule is presented in the bulk of the fluid medium in such a way so that in its surrounding the same nature of molecules are present and all the molecules are having almost equal spacing from this particular molecule. So in this scenario, what will be happening? This molecule will be receiving equal amount of attraction forces from all the sides and ultimately the net force will be balanced. But if I go for a molecule which is present at the boundary between the two fluids, there you will be finding that this molecule, say this fluid 1 is some high density fluid and fluid 2 is low density fluid. So first point is that here the number of molecules which are present, these will be more, and here number of molecules experienced by this may be sparsely spaced. Second important point is, if you take the example of water and air, so in this scenario you will be finding that in case of here mostly the molecules will be neutral and the effects of attraction forces will be majorly due to the dispersive or inductive effects. On the other hand, if I talk about water, this is a polar molecule where permanent dipoles are existing. So here majorly the forces will be coming because of the electrostatic forces. Now you can see in a molecule where always permanent charge is existing, that will be leading to stronger forces in comparison to the molecule where charges are actually fluctuating and are of small magnitude. Okay. So in that scenario, you will be finding that the attraction forces on this molecule from the surrounding water molecules will be stronger, whereas the forces from the fluid 2 molecules will be less in comparison to this molecule. Okay. So under this scenario, what will be happening? In the top portion magnitude of forces is less and in the bottom portion magnitude of forces is more. So ultimately this molecule is subjected to a permanent force which is trying to move the molecule in which direction? Downward direction. Okay. So because of this effect, typically we observe that near the interface, below if this much is spacing of molecules, close to the interface the intermolecular spacing is slightly larger in comparison to the spacing in the bulk portion. Okay. So now what typically happens when this net effect tries to move the molecule in downward direction, the spacing between the molecules becomes small, and because of this small spacing, whatever the net downward force is acting on this molecule, that is balanced by the repulsive forces which have started occurring because of the decrease in intermolecular spacing. Is this point clear? So ultimately the repulsive forces, because of decrease in these spacing, these will try to balance this downward force and this will try to make the molecules stay at this location. Okay. So once this molecule is staying at this location, you can see it is always in the condition of, it is always in the unhappy state. See, everything, if you are sitting over here in a stable situation, you will always be comfortable and you don't want to move anywhere. But if I ask you that you are hanged through this roof, so ultimately your tendency will be as soon as you are reaching to your stable condition. So ultimately the point is the molecule which stays in bulk of fluid, because these are receiving equal amount of forces from all the sides, these almost stay in their comfortable and happy state. But molecules which are close to the interface, free surface, these typically tries to come towards the downward direction and this downward motion is actually balanced by the repulsive forces which are generated because of the intermolecular distance, and ultimately these molecules have to stay over here. But whenever this molecule is staying over here, this molecule is also receiving some tension force along the interface. So it means it is always in the state of unhappy. And overall outcome is that whenever you will be finding that all the short range forces are actually trying to participate over here in order to make these molecules stay at the interface. Okay, and attractive forces in the surroundings, particularly in this direction, these are of same nature. So here typically the net effect is that our interface, the molecules near the interface are always subjected to some net amount of force which is called as surface tension force. Okay, so how surface tension force is manifested, that let us try to understand with the help of this simple experiment. So here we have a 3-bar arrangement, and in this 3-bar arrangement we do have one more bar, and this particular bar is actually movable, whereas the other 3 boundaries of this particular structure, these are fixed. Now if I generate a liquid film over here, so this is nothing but a liquid film, and this liquid film is formed in between these 3 bars and this movable bar. Okay, now what will happen if I simply do not pull this bar? Ultimately what will be happening? This bar will try to move in this direction and film will try to collapse. In order to maintain this liquid film, what we need to do? We need to hold this bar with some force. So whenever we are holding this bar, let us consider I am applying F amount of force in order to hold this bar at its current position. So ultimately, if L is the spacing between these plates, what is happening over here? What I told you, that if I remove this force F, then this bar is moving in this direction. So ultimately there is certain amount of force which is acting in this direction, and to balance that force I have to apply F amount of force so that bar can remain in the static condition. Okay, so whatever that force which tries to pull back the bar and decreases the surface area of this liquid film, that particular force is something which we call as surface tension force. Okay, now surface tension force is determined with the help of surface tension coefficient sigma, which is defined in the form of force per unit length. How you can estimate this? Let us consider that, as I told you, L is the length. So if sigma is surface tension coefficient, then how much will be the force which is acting because of the fluid? So force which is acting because of the fluid, that will be sigma into L. And now you have to understand this point. Whenever I am considering the bar, this particular bar will also be having certain thickness in the direction normal to the board, and of course whatever the liquid film we are having, that liquid film will also be having 2 interfaces, one interface from top side and one interface from the bottom side. So ultimately the force because of the surface tension which is acting on this, that will be 2 sigma into L, and this force has to be balanced by this F. In that scenario only I will be able to maintain this liquid film at the current situation. So it means that from here sigma will become F by 2L. Now one important point is that what is happening whenever I am removing this force, this needle is coming back and moving backward. So once needle is moving backward, what is happening? the surface area of this exposed surface area is actually decreasing. Okay, so if exposed surface area is decreasing, what it means? It means the number of molecules which are close to the surroundings of air, these will be decreasing, and in order to maintain the volume constant, the thickness of the liquid film will be increasing. So if thickness of liquid film will be increasing, it means some of the molecules are coming from free surface towards the bulk. Is this one clear? So the natural tendency of the molecules which are staying at the interface, their natural tendency is always to move from the interface towards the bulk. Is this one clear? Because this simple experiment shows this thing only. If I remove the force, this needle will be moving in backward direction. Say after some time t it will be here, then after some time t2 it will be somewhere over here. So whenever it is moving in backward direction, ultimately what is happening? The area exposed with the surrounding air of this liquid is decreasing, and in order to maintain volume constant, then the thickness of the liquid film will be increasing. So it means whatever the molecules were there earlier in this portion, these molecules have now entered into the bulk of the liquid. So this simple experiment shows that whenever a liquid or any other type of fluid is exposed in the surroundings of other fluid, it does not want to, molecules of that particular fluid does not want to stay at the interface. The tendency of the molecules is always to come towards the bulk so that they can come into the stable condition. Okay, so we have to apply certain amount of force against which these molecules stay close to the surface. This simple example is, if you consider a drop of water, so what happens? In a drop of water, all the molecules will be having tendency to come from interface towards the bulk. But ultimately, in the center of the drop, we have more pressure in comparison to the pressure at the interface or in the outer side, which is trying to balance that surface tension force and makes the molecules stay near the interface. Is this point clear? Now, typically what happens, let us consider that this is my liquid column. Okay, and this liquid column I have splitted it into two portions. So this type of breaking I have done. Okay, so once I have broken this into two portions, what has happened? There is formation of a new surface, and this surface is now exposed to surrounding fluid, and there is one surface which has formed at the bottom, and this surface is also exposed to surroundings. Okay, so in order to break this liquid column into two parts, what I have to do? I have to invest certain amount of energy. So energy invested in breaking these breaking this liquid column has to be equal to the final energy state of this liquid column. So what will be its final energy state? Sigma L is the surface tension coefficient, and how much area we have created? Let's say A amount of area I have created. So sigma L into A from one side plus sigma L into A from the other side, and ultimately I will be getting EC equal to sigma L, 2 sigma L into A. Is this one clear? So what I told you, this is the amount of energy which I have invested on breaking the liquid column. This liquid column in the top side and the bottom side was having same type of molecules. Okay, so it means these molecules were of same nature. So the forces which were acting on these molecules, these were of equivalent nature. So it means these molecules were of cohesive nature. So over here, whatever energy I have invested, I can call it as cohesive energy. Is this point clear? Okay, so whenever we have made the efforts to break the molecules of, to break the column of same type of molecules, then whatever the final state of energy we have obtained, that final state of energy will be equal to the cohesive energy. So whenever, one important point we have to consider, whenever we determine the surface, when we determine the interfacial energy or cohesive energy per unit area, then whatever quantity we get, we call this quantity as surface tension. And typically surface tension is calculated whenever we are considering the cohesive forces in the surroundings of air only, majority of times in the surroundings of air only. Okay, so whenever we determine cohesive energy per unit area, particularly in surroundings of air for a liquid medium, that value we call as nothing but our surface tension. Typically, the surface tension of a liquid medium or any other fluid medium changes with the temperature. How? You can see this is the equation which is called as Idvos equation. As per this equation, sigma L into V power 2 by 3 is equal to C times Tc minus T, where V is the molar volume of that particular fluid and C is a constant. Typically for many liquids, the value of C is 2.1 into 10 to power minus 4 joule per Kelvin. From here you can see that, and what is this Tc? Tc is known as critical temperature. So can you tell me what is the critical temperature of a fluid medium? We study in thermodynamics.
Liquid, solid and gas all present.
That is triple point temperature.
Liquid and gas is present.
So the temperature at which saturated liquid line and saturated vapor line actually meets. Okay, so that particular temperature is called as critical temperature. If I give you some example, this will be your TS diagram. On TS diagram, this is my saturated liquid line, this is saturated vapor line, and the point where both these lines are meeting, that is called as critical point. So you have to understand that below critical point I will be having separate existence of liquid as well as the vapor, but whenever I will be reaching or moving above the critical point, then ultimately what will be happening? Can you tell me how constant pressure line moves over here? So this is how constant pressure line is there. So you can see below this point I have subcooled liquid, here I am having saturated liquid, in between the dome I will be having mixture of liquid plus vapor, and above this point I will be having superheated vapor. Okay, but if you consider a pressure line which is moving through this critical point or above the critical point, what will be happening? For these pressure lines, can you separately define where is liquid, where is vapor? Okay, so typically above the critical point, our state of the substance becomes such that we cannot make clear distinction between the liquid and the vapor unless or until we are physically verifying it. Or in other words, if whatever vapor state we have, the molecules in the vapor state will also become so close to each other that their intermolecular spacings will be becoming identical to that of the intermolecular spacing between the liquid molecules. Is this one clear? So typically when you will be referring to the basic thermodynamics books, so majority of the books tells that above the critical point we typically mention our state as dense fluid. Why dense fluid? Because unless or until we physically verify, we will not be able to find the gap in between liquid and vapor. And second important point is that even if fluid is existing in the vapor state, pressure is so high that the intermolecular spacing in between the vapor molecules will be excessively small. So this will also be behaving very dense vapor medium. So typically you can observe that whenever your surface tension, when it comes into picture, it typically comes into picture when intermolecular spacings are different, the way I explained you previously. For example, in bulk of the liquid, molecules were closely spaced, so these were facing from all the sides attraction forces. But when we have come near the top, then molecular density as well as the nature of molecules have changed, and ultimately what we observed, we observed that the forces were asymmetric. Okay, because the magnitude of the forces in the top portion were less and in the bottom portion were more. Moreover, earlier example I gave you about air and water. But even if I consider that, here I am having liquid of water and there I am having vapor of water. Now again what I am having? I am having the same nature of the molecule. So that's why electrostatic, inductive and dispersive effects, these will be remaining almost the of similar nature, but ultimately what is happening? The number of molecules which are present in the surrounding of this molecule and the number of molecules which are present in the surrounding of this molecule, these will be different, and because of this there will be again some amount of surface tension in this scenario as well. Okay, is this point clear? But if I say that I have reached a situation where packing density of the molecules of vapor has also become identical to that of packing density of the molecules present in the liquid, in that scenario, for same nature of molecules, the surface tension force at the interface will actually vanish. So that is the reason typically in this equation you can observe that the right hand side is having Tc minus T. So it means that whenever your temperature is less than Tc, then your magnitude of surface tension coefficient will be large. But whenever you are approaching towards the critical point, then magnitude of surface tension force is decreasing. Okay, so the reason is because at that point we will be having existence of a fluid medium which will have identical intermolecular spacing or identical molecular packing in both liquid as well as the vapor mediums. Is this point clear? So another equation which explains the variation of surface tension of liquid with critical temperature can be given by this: sigma L equal to sigma naught into 1 minus T by Tc power n. Okay, so typically sigma naught is a constant to the liquids and n is equal to 11 by 9 for many liquids. So this is how you can see the way you determine variation of density, variation of viscosity and variation of say thermal conductivity etc. with temperature. In the similar way, using these equations you can determine the dependence of surface tension with temperature. Is this one clear? Now surface tension is a property because ultimately why it is coming? It is coming because of the charges and the molecular effects. Okay, so it's a property which is very sensitive to the presence of impurities at the interface. Okay, it means that if you have some pure air water interface, then you will be having under atmospheric conditions, then you will be having sigma equal to 0.07286 Newton per meter. But if you have some impure air water interface, it means some dust particles are actually collected near the interface between the air and water, you will be finding that drastic decrease in surface tension. Okay, why? Because these dust particles will try to disturb the charge as well as the molecular arrangement near the interface, and this property is mainly manifested because of the molecular forces. Okay, so here you can see two examples where we have added NaCl in water, and this NaCl is added in the weight percentage ratios of 10%, 20% and 30%. And typically if you observe the value of surface tension, it is almost remaining constant. Okay. On the other hand, if instead of NaCl you add propanol to the water, and then if you see, you have drastic decrease in the surface tension. Okay, so here you can observe that typically whenever a solute is added, it depends upon the tendency of the solute to either concentrate in the interface or to get mixed with the bulk of the fluid. Okay, so whenever we have added the NaCl, it's a electrolyte solution. So typically electrolytes have good miscibility with the polar molecules. So electrolyte will try to stay in the bulk of the water and it will not stay near the interface. So ultimately, as NaCl molecules have mixed with bulk of water and these does not have stayed at the interface, so ultimately there was no change in the surface tension. But on the other hand, whenever I have added the propanol, it's a organic solute. So typically the organic solute is of hydrophobic nature. Okay. So what is the meaning of hydrophobic nature? It will try to stay away from water. So if it is trying to stay away from water, it will get collected near the interface. So once it is getting collected near the interface, at the interface now the molecular arrangement has changed, because of which you will be finding that upon inclusion of propanol we have significant decrease in the surface tension. Is this point clear? Now you can see one more solution, which is cetyl trimethyl ammonium bromide, and whenever it is present in phosphate buffer solution. So you can see the weight percentage. Earlier, how much weight percentage we have added? Significant amount of solution we were adding. Okay. Now this CTAB solution I have added in the range of 10 to power minus 6 weight percentage, minus 4 and minus 2 in very small amount. And you can see upon adding this, there is significant decrease in the surface tension, and after some critical point upon further addition there is no change in the surface tension. Okay. So typically when an organic molecule has polar part and hydrophobic part, both parts are present, then ultimately what will be happening? The hydrophobic part will try to repel it from the bulk, and polar part will try to change the surface tension. Polar part will try to significantly alter the molecular forces near the interface. So under these scenarios, we will be finding significant variation in surface tension upon addition of that particular substance in extremely small amount. So here you can see such amphiphilic molecules are typically referred to as surface active agents or surfactants. Okay. So what we do in case of while washing clothes, we add some detergent powder. So ultimately what it does, it also try to decrease the surface tension force. Now comes another aspect. So here what we have liquid 1 and this is liquid 2. Two different liquids which are staying close to each other. So of course the molecules which are present over here, these molecules will be having different amount of forces from top and bottom. Okay, because the molecule presented are different on both the sides. So because of this, at this surface, say sigma AB was the interfacial tension. Okay, so typically you have to remember one thing: whenever the surface tension coefficient is measured in the surrounding of air, then it is called as surface tension. But whenever the same coefficient is measured in the surrounding of some another liquid, then it is called as interfacial tension. So here what I am saying, I have one liquid 1 and other as liquid 2. So it means this particular interface is not in the surrounding of air, but it is in the surroundings of some another liquid. So that's why I will be calling this coefficient as interfacial tension. So this interfacial tension is sigma AB. Now if I have added certain amount of energy to break this interface into two parts, so what I will be getting? I will be getting one interface of A type of fluid which is exposed to air, and here I will be getting one same interface of same area of some other type fluid B which is again exposed to air. So I can see the final energy state will be sigma into A plus sigma B into A. This is the final energy state. What was the initial energy state? Initial energy state was sigma AB into A plus how much amount of energy we have invested to break this. So say the amount of energy we have invested to break this is EA. Is this point clear? So what is EA? EA over here is called as adhesion energy. Why adhesion energy? The forces which acts between the different type of molecules, these are called as adhesive forces. So ultimately over here you can see one is fluid A, other is fluid B. So we have broken the boundary between these two different type of molecules. So that's why we will be calling it this as adhesion energy. Okay. Now for majority of the liquid combinations, if I have one liquid in the presence of other liquid, the value of sigma AB will be very small in comparison to the surface tension. So typically the interfacial tension is of small magnitude than the surface tension. However, the estimation of interfacial tension is a challenging task. Theoretically, it is extremely difficult to determine interfacial tension. So from this point you can see that if you have to theoretically determine, first thing is you must know the individual surface tensions of the two liquids which are participating. Other than that, you have to also determine the amount of adhesion energy. Okay, so which is extremely challenging to calculate. So that's why for estimating epsilon A, majority of the time we have some empirical relations, and these empirical relations just involve the functional dependence on individual surface tension sigma A and sigma B. Okay, and then using this information from empirical relation and individual surface tensions, we can calculate the value of interfacial tension. However, there are certain experimental ways to calculate this. What are these experimental ways? Of course, our interest is to study these. So now, as I told you, because for common fluids, typically the surface tension data will be available, but the understanding of interfacial tension will be actually difficult from the theoretical analysis. So that's why we have to devise certain methods to calculate surface tension or interfacial tension. So some of the methods are, typically these methods are categorized into two ways. First category is force methods and second category is drop shape methods. In force methods, the sub methods are drop weight, ring method and Wilhelmy plate method. And in drop shape method, we will be talking about pendant drop shape, rotating cylinder method and maximum bubble pressure method. So let's first try to see the very first type of the method. In this one, what we have done, this is drop weight method. We have a container, and in this container, in the surroundings, we have air. Now what I have done, I have taken a needle, and in this needle, I allowed the liquid to freely fall under the effect of gravity. Okay. So in this scenario, what will be happening? If you have a very thin needle and if you observe when water comes out of the needle, how it comes? Initially, it comes in the form of a small bubble, a small drop, and slowly the size of this drop keeps on growing. And after a certain point, this drop just leaves the surface of the needle, okay, and it freely falls. So whenever this drop is freely falling, you can see the weight of the drop is acting in downward direction, and just at the verge of free fall you can observe that it was holded at the periphery of the needle. So at the periphery of the needle some force was acting, which is nothing but our interfacial tensile force, okay. Now the drop, whenever just drop is about to leave, corresponding to that point we can say that the magnitude of the interfacial force will be just equal to the weight of the drop, okay, because when magnitude of interfacial tension was more than the weight, then this drop volume was just keep on growing, but once it has become equal, after that drop will be falling in the downward direction. So I can balance WD, which is the weight of the drop, with 2 pi r. R is my radius of the needle. So 2 pi r will be circumference, and at this circumference only it is contacting. So that's why 2 pi r into sigma L, where sigma L is surface tension coefficient, and along with that I have multiplied some factor Fw. So Fw is actually the shape correction factor. So typically whenever a drop is hanging from the needle, there can be slight differences in the circumference because of the some imperfections, okay. So that's why we have to account for some correction factor, and correction factor typically is given in the form of radius of the needle divided by volume of the drop power 1 by 3, and you can see r by v power 1 by 3, and this is the value of correction factor. So when r by v 1 by 3 is 0, then correction factor is 1, and when this value is increasing, these are the different values of correction factor, okay.
इंटरफेशियल टेंशन तो तब बोलेंगे ना जब अगर सराउंडिंग में फ्लूइड एयर के अलावा कुछ है।
Yes, so why this common terminology is used? Because whenever I will be doing it in the surrounding of air, then it will be surface tension, but I have also shown you the second representation. So that is when in the surrounding I have some other fluid. So then a more generic methodology, more generic terminology will be interfacial tension.
तो फिर सर इस मेथड से अपन तो मतलब इंटरफेशियल टेंशन फोर्स भी निकाल सकते हैं।
Yes,
बट
yes.
अभी आपने बोला था कि इंटरफेशियल टेंशन फोर्स मतलब कैलकुलेट करना डिफिकल्ट है।
Theoretically calculate करना difficult है, but experimentally you can calculate. So that is the point, that theoretically it is challenging to determine the adhesion amount of adhesion energy. So that's why we will try to devise some experimental ways to determine the interfacial tension, okay. And here this is liquid, this is fluid. One important point you have to keep into account: whenever we are measuring the interfacial tension using this method, we have to use these fluid combinations in such a way so that this fluid is of lighter density in comparison to the drop liquid. This always has to be of higher density, okay. So using this method, of course, if you measure the weight of a single drop, that will always be difficult to measure because it will be very small, and it will not be, weight measurement will not be precise even if you take your weight measurement system of the sensitivity up to micrograms. So that's why what is done, this platform is placed on some, this platform is typically placed on the weight measurement system, and this weight is counted for, say, number of drops which are leaving the needle. Say it can be counted for 10 drops or 50 drops, and accordingly here WD divided by that number factor is actually used. Because if you try to measure it for a single drop, then ultimately the uncertainty because of the experimental measurements will be more. So typically when you do perform the experiment, you measure the weight either for, depending upon the density of the liquid medium and the precision of your weight measurement system, you have to count that whether you are measuring the weight for 10 drops or 50 drops or 5 drops, depending upon the density and the precision of the weight measurement system. And this can be used for measurement of interfacial tension, as I already discussed, but only thing you have to keep into mind that this has to be heavy fluid and this has to be a lighter fluid. Second important point is, whenever we have done this force balance, I have not accounted over here the buoyancy force. Okay, so typically when I am having air and water combination or any liquid and air combination, then density of air is extremely small in comparison to the density of the yes. So that's why there we can neglect the buoyancy force. But ultimately, whenever you are considering the different fluid combinations which are having comparable densities, then we have to also take into account the effect of buoyancy force to correctly measure the interfacial tension. Otherwise, our measurements will be wrong. Is this one clear? Okay, so other methods we will discuss in the next class.